Good morning everyone. Welcome to the lecture 3 of this engineering mechanics course. In the previous lecture, we solved numerical problems on fundamental principles of forces where we learned how to resolve the forces, finding the resultant and determining the direction of the resultant forces. In today's lecture, we will extend the understanding to concurrent force systems in a plane using free body diagrams and equilibrium equations. So what is a free body diagram? Before going with the free body diagram, we should know what is a free body. A free body is a body which is isolated from all its connecting medium. So the diagram representing all the forces acting on the isolated body is called a free body diagram, commonly represented as FBD. While drawing an FBD, we should remove all the supports and contacts. We should replace them with the reaction forces and show only external forces acting on the body. Let us see a parrot is sitting on a support. We can take the support alone. This support has been hanging with the two strings and the weight of the parrot is acting vertically downwards. Right, since the weight is acting downwards, the strings will give the opposing force in the upward direction. Let it be T1 and T2. So this is what is the representation of the free body diagram. So since W would have been known, we can able to find out the tension developed in the first string as well as in the second string. So one more example, you can see a signal light is being hanged by using the strings A, C and B. Right? So representing the joint C as a free body, we can represent two strings, tension in the portion CA as well as CB, and the weight will be suspended in the vertical direction at a point C. That's what I can see. Before which we can take the light also one free body. So the weight of the light will be acting downwards and the tension which is acting in the portion CD will be calculated applying the vertical force equilibrium. That is nothing like weight of the light itself. Next, moving on with the joint C, we will have the tension in CD portion, tension in CA portion as well as tension in CB portion. Since the tension in CD portion is known, we can able to find out the tension in the portion CA and CB by either applying the resolution of forces concepts or by using the Lami's theorem approach. So without a correct free body diagram, equilibrium problems cannot be solved. So let us move with a numerical problem. A wheel shown in figure has radial spokes that are equally spaced, all assumed to be in tension. If 500 Newton, 700 Newton and 600 Newton respectively are the tensions developed in the first three consecutive spokes, estimate the tension developed in other spokes. So they are given a wheel in which 5 spokes being given radially. And it has been given all the forces in the spokes are in tension, which means that the forces will be acting away from the contact point. That's what the direction has been mentioned. So the tensions in the three consecutive spokes being given as 500, 700 and 600. Let us first understand the geometry. So since the spokes are equally spaced, the angle between the consecutive spokes will be 72 degree. That is 360 divided by 5 will come 72 degree. And all the forces acts away from the center of the wheel as they are in tension. And the forces are concurrent at the center. Let the unknown forces be F1 and F2. And one more thing, we can take these forces from any spokes in a radial direction. But if any problem has been given without giving the forces in the given figure itself means you can assume any one point as the base. Let me assume this is the base, 500 Newton. And the second force will be given here, 700 Newton. Third one will be 600 Newton. And the unknowns, let me take it as F1 and F2. So now let us draw the free body diagram of the wheel center. Before going with that one, we are supposed to find the x and y component of all the forces, because all the forces are not acting in a single direction. So that we'll be applying the resolution of forces concept. So similar to the previous problem, what we done in the previous lecture, we are not going to apply the resolution of forces with respect to the nearest x-axis and y-axis. Let us try with a new approach in which we'll take one axis as a reference axis for all the forces. Let me assume this is the axis, the reference axis as the benchmark for all the forces. Either it may be for x direction or it may be for the y direction. Let me assume this is the reference axis. And we'll start with the 500 Newton. So 500 Newton force is acting along that axis itself, which means that 500 Newton force makes an angle of 0 degree with respect to the benchmark axis. Now 700 Newton force. So 700 Newton force makes an angle of 72 degree with respect to the benchmark axis. 600 Newton, coming with the 600 Newton force, the angle of this 600 Newton with respect to the benchmark is, that is, will be taking in this direction, and this angle will be 72 plus 72, which comes as 144 degrees. If it is the previous case, means we would have taken that 600 degree with an inclination of 36 with respect to the x-axis. But instead of going with the conventional approach, let us try with a new approach in which one axis will be taken as a benchmark for all the forces, both for x-axis as well as for y-axis. Now F1 will make an inclination of 72 plus 72 plus 72, which comes around 216 degree with respect to the benchmark axis. That is this one. This is 216 degree. And finally, F2 will make an inclination of 288 with respect to the benchmark axis. So now, one more thing is that previous cases and all will be checking the direction of the forces. For example, if I am taking this 700 Newton force, the resolution will becomes y component will be acting vertically upwards, x component will be acting horizontally in this way. Let me go with the 600 Newton, vertical component will be acting upward, horizontal component will be acting left side. Similarly, F1 and F2 also will be doing. But in this problem, rather than resolving all the forces individually and to find out whether it is a positive or negative, we are going with a different approach. So in this case, we are not going to consider whether it is a positive or negative. And we are not going to resolve the forces with respect to the near x-axis as well as y-axis. But one condition it should satisfy is all the forces should act away from the contact point. That is what has been satisfied in this case. So let us solve this one. The x component will be 500 cos 0, which means 500 itself. The y component of the 500 Newton force will be 500 sin 0, which will become 0. Next, going with the 700 Newton force, which makes an angle of 72 degree with the benchmark axis. So in that case, it will be 700 cos 72 is the x component and 700 sin 72 will be the y component. Next is the 600 Newton force. The angle made by the 600 Newton force with respect to the benchmark will be 144 degree. Therefore, x component of that force will be 600 cos 144 degree and y component will be 600 sin 144 degree. Note that x component of that 600 Newton force, if it's a conventional way in the sense, you would have mentioned it as a negative sign. But since we are taking from the reference axis, we are taking everything as a positive value rather than considering separately positive or negative. Next, moving on with the F1 force. F1 makes an angle of 216 degree with respect to the benchmark axis. So x component will be F1 cos 216 and y component will be F1 sin 216. And finally, F2 will have the x component as F1 sin 288 and y component will be F2 sin 288 degree. Now, under the equilibrium conditions, the summation of forces along the x direction will be equal to 0 and summation of forces along the y direction also will be equal to 0. So write the equation summing up all the forces along the x direction equated to 0, let it be equation number 1, and summing up all the forces along the y direction equated to 0 and make it as equation number 2. So we have two simultaneous equations with the two unknowns of F1 and F2. So solve these two simultaneous equations, we can get the value of F1 and F2 as 561.8 Newton and 723.61 Newton respectively. So this problem clearly demonstrates the power of resolution of forces in concurrent systems. Let us move with the second problem. This is a classical problem. Either it could have been given like a 2 cylinders or 3 cylinders placed in a container. So here 2 cylinders A and B of radii 75 mm and 50 mm and weighing 100 Newton and 75 Newton respectively are placed in an open rectangular channel as shown in figure. Determine the reaction developed at each contact points. This is what the problem. So we have 2 cylinders of radii 75 mm and 50 mm. Their weights are 100 Newton and 75 Newton, which are placed in an open rectangular channel. So we are supposed to determine the reaction at each contact point. Right. So before we can see that how many contact points are there. Let me have this cylinder is having the contact with respect to the vertical wall as well as with respect to the ground. So it will have two contact points. At two contact points, reactions will be developed. And one more thing, this cylinder is having a contact with the cylinder B also at this point. So we'll have the reaction at the third point also. Let it be 3. And finally, going on with this container, that is this cylinder B, this is having contact at a third point as well as one with respect to the vertical wall, that is given as 4. Let me connect the 2 points O1 and O2 to form a triangle, making it as O1, O2 and P, which makes an inclination of theta with respect to the horizontal. I'll tell this one what is the need of drawing this triangle. Now let us draw the free body diagram of both the cylinders separately, cylinder A and cylinder B. So let us start with the cylinder A. So the forces acting will be the weight, which will be acting vertically downwards with a value of 100 Newton. So normal reaction at all contact points, we have 1, 2 as well as 3. And don't forget normal reaction. The name itself we can see normal reaction, which means that these forces will be acting perpendicular to the contact surface. So here the contact surface is a vertical surface. Therefore, the normal reaction will be acting perpendicular to the perpendicular to the vertical wall. And one more thing, the second surface is a horizontal surface. So normal reaction will be acting vertically upwards, perpendicular to the surface. And going on with the third point, it is not having a surface, it is having a contact point. So in that case, we can draw a tangent connecting that point, and then perpendicular to the tangent only will be getting the normal reaction. So these are the three normal forces which will be normal reactive forces which will be acting on cylinder A. Let us represent in the free body diagram. So we have N2 which will be acting vertically upward, and then we'll have N1 and finally N3. All the forces will be acting towards the center point because they are the reactive forces. Next we shall move with the cylinder B. Again here also weight will be acting vertically downwards of magnitude 75 Newton. Then it is having two contact points 3 and 4. So again representing the normal reaction towards the center point will be getting N4 and N3. Now you can see that N3 is an inclined one which makes an inclination theta with respect to the horizontal. So we should know this value theta, which has not been given in the problem. So for that case only we are representing a triangle connecting the center points of the two cylinders. If it is a 3 cylinder, you can connect all the 3 center points. You can form a triangle. And then we can use the triangle approach for getting the unknown angle. Now let us go with O1P, which is equal to, we can see this is the radius. That is O1 is the radius of this cylinder. that is 75. This is 75. And similarly, P and this point, the radius is this one, that is nothing like this one, O2 and 4. This is 50. So total is 200 mm. We need O1 P only. So in that case, it will be 200 minus 75 and minus 50. You will be getting 75 mm. That is what is the horizontal. Next, one more side also we should know, then only we can able to calculate the theta. In any case, whether it may be a 2-cylinder approach or a 3-cylinder approach, vertical distance is impossible to find it out. And then we can go with the diagonal. So diagonal represents the connecting the center points, which means that O13 is the radius of this cylinder and 3O2 is the radius of this cylinder. Since the radius of both the cylinders are known, we can easily find out O1, O2, which will be equal to 75 plus 50 equal to 125 mm. Now taking theta, opposite side is unknown, adjacent side is known, as well as hypotenuse is known. So we can use the cos formula. So theta will be equal to cos inverse of 75 divided by 125. We'll get angle as 53.13. So now we got the angles and we already drawn the free body diagram. Next, easily we can apply the resolution of forces to solve for the unknowns N1, N2, N3 and N4. Now let us start with the cylinder B. Why we start with the cylinder B is here we have only two unknowns N3 and N4. Whereas if you are going with the cylinder A, we will have N1, N2 and N3. Three unknowns will be there. But we have only two equilibrium equations, Fx equal to 0 and Fy equal to 0. So it is impossible to solve for the unknowns if you are starting with the cylinder A. So that's why we are starting with the cylinder B. So now write the equilibrium equations Fx equal to 0 in which N4 is acting in the horizontal, pure horizontal direction and is acting in the left side direction. So it will be minus N4. Whereas N3 resolving this force means we will be getting, this is the horizontal and this will be the vertical. So horizontal will be positive direction. An angle is given with respect to the x-axis itself. So in that case it will be N3 cos theta positive. So N3 cos theta. And theta has been already calculated. Similarly, go with the vertical component Fy equal to 0. So in that case, we have this N3, the vertical is acting upward. So it will be positive. An angle is given with respect to x component. So y component will be sin theta. So N3 sin theta upward positive and the weight is acting vertically downward. So it should be negative. So N3 sin theta minus 75 which will be equal to 0. Keep this as equation number 1 and 2. So solving these equations with the value of theta of 53.13 which has been solved earlier, we'll get the value of N3 and N4 which are 93.75 Newton and 56.25 Newton. Now let us move with the cylinder A. So here we have three unknowns N1, N2, N3 in which N3 has been calculated now with the help of the free body B. In that case we have only two unknowns N1 and N2. So write the equilibrium equation starts with Fx equal to 0. Here N1 is a pure horizontal force and N2 acting in the positive direction. So it will be N1 itself. Whereas N3 is an inclined force acting towards the joint. So in that case, resolving this force, it will be acting vertically downwards and like this. So x component will be a negative since it is acting towards left side. An angle is given with respect to the x-axis. So in that case, N3 cos theta negative sign. Whereas this N2 and 100 Newton are purely vertical force, it will not have any influence on the x component. So that's why x component will become N1 minus N3 cos theta will be equal to 0. Let it be equation number 3. Then we'll move on with the y component. So in that case, we'll have N2, it's acting vertically upward, that is positive. And then we have N3, if I am resolving along the y direction, it is going downward, so it should be negative. So minus N3, angle is given with respect to x-axis, so y component should be sin theta. So minus N3 sin theta. And the weight is acting vertically downward, so it should be minus 100 equal to 0. Let it be equation number 4. Now again you can see we have two simultaneous equations with the two unknowns N1 and N2. Since N3 has been already found out 93.75. So substituting that values, we can get the value of N1 and N2 which are 56.25 Newton as well as 175 Newton. This is what is the solution for this problem. Let's move with the final problem in this lecture. So we have a figure shows the cylinders A of weight 100 Newton and of B of weight 50 Newton resting on smooth inclined planes. They are connected by a bar of negligible weight hinged to each cylinder at their geometric centers by smooth pins. Find the force P as shown that holds the system in the given position. So we have two cylinders A and B which are weighing 100 Newton and 50 Newton. They are resting on smooth inclined planes and they are connected by a light bar hinged at their centers. The question is we need to find the force P required to keep the system in equilibrium. So we shall draw the free bodies for cylinder A and cylinder B. So for each cylinder, show that weight will be acting vertically downwards, normal reaction from the plane, force in the connecting bar as well as the applied force. Let us draw the free body diagram for A, cylinder A. So the weight will be acting vertically downwards. Let it be WA. It is known 100 Newton. And then we have the normal reaction from A. It's been given. As well as we have one more thing is the bar which is giving a force acting towards the joint. If this is acting downwards in the sense this cylinder will tends to slide downwards. So that is the reason it has been given opposing force, upward direction. So we have let it be Q. Okay, that makes an angle 15 degree with respect to horizontal. Let us move with the free body diagram B, in which the weight will be acting vertically downwards, and then we'll have the reactions from the surface. Let it be NB, and then the compressive force which will be developed from the bar Q, and the externally applied force P makes an angle of 60 degree with respect to the vertical. Okay, so free body diagrams are known. Just we can apply the equilibrium equations to solve for the unknown P. Now let us start with the block A, because in block B only the unknown is available. And in block A we have NA and Q are the two unknowns. We can solve for it. So applying the force equilibrium Fx equal to 0, we have NA resolving. It's an inclined force. Resolving means this is the x direction and this is the y direction. So x will be positive, y will be positive. Angle 30 is given with respect to the x-axis, and similarly y is also an inclined force. The x component will be acting like this, y component will be acting like this. So x will be negative, y will be positive. Again angle is given with respect to x-axis. So in that case we will have NA cos 30 minus Q cos 15 will be equal to 0. Let it be equation number 1. Now vertical force equilibrium will have NA sin 30, because angle is given with respect to x-axis, y component will be sin 30, and then Q again angle is given with respect to x-axis, y component will be sin. So Q sin 15, and the weight is acting vertically downward. So minus WA will be equal to 0. Since WA is known with the value of 100 Newton, solving these two equations we can get the value of NA and Q. Next we shall move with the free body B. Again here also this is nothing like P, it's been missing. So solving this one, x-axis and y-axis, here Q horizontal is acting like this, vertical will be acting like this. NB horizontal will be acting like this, vertical will be acting like this. Similarly P horizontal will be acting like this, vertical will be acting like this. So based on this one we can fix the signs positive or negative, and except this P, both Q as well as NB has been given with the inclinations with respect to x-axis. So x components of Q as well as NB will be cos theta, whereas y components will be sin theta. On the other hand, P, the angle is given with respect to y-axis. In that case, y component will be cos theta and x component will be sin theta. So substituting all the values, we'll be getting the value of NB and P, in which P is the unknown which has been asked to find out. So we are getting the value as 26.79 Newton. So to summarize today's lecture, you should always start with a correct free body diagram. You should identify all the forces clearly, resolve the forces into their components, apply the equilibrium equation systematically, and solve numerically without skipping any steps. So this method forms the foundations for trusses, frames and structural analysis. So in the next lecture, we'll continue with the concurrent forces in plane applications as part 2, solving some other numerical applications. Thank you.